And that's what basically called network control systems. So all the distributed systems essentially has a network. Okay? So you can see that in a very simplified, you see there is an actuator, there is a physical system. The physical system has a sensor. You sample that, you quantize that information. You see that dotted line in between is the network. So you can see that this is the network in the middle, and you have the wireless or wired, the delay and packet losses, and you have a controller in the feedback loop, and you have a control quantizers. So the controller is outside the feedback loop, and then it goes through the network again, and it basically becomes a packet goes to the actuator here. So the network is in between the physical system and the controller. Such a system is called network control systems. It's connected through the network. So when such a system exists, you have issues like network control system. You have packet delays. If I can find my mouse here. So you can see that there is the network induced delays. Okay, so the delay, you see that the taus are called delays. Then you have packet losses. The gammas are packet losses. And then the quantization errors. So what happens is when this measurement value, temperature like 50 degrees, that's quantized when it goes to the network. Quantized means it has finite number of bits. There will be round of errors. And that information goes and becomes a packet. So that's what is called quantized errors. So if you see that at the bottom, you see that you transmit the sensor, it takes so many seconds to receive it at the controller. Controller generates a packet, it takes so many seconds to reach the actuator. So this time is called the round trip time from the sensor all the way to the actuator. And that time is random. So sometimes that packet gets dropped. So when the packet gets dropped, the network when the network control system operates in what? When the packet gets dropped, what will happen? It will not transmit. So physically it becomes what? Open loop. It becomes open loop. Even though you are physically connecting a network, there's no information going in. It becomes open loop. Now, I know most of you have some controls background. Why do we always prefer closed loop control system? And why do we like closed loop control system? Why not run the system open loop? Right. So there is a performance. So you look at a performance. Why open loop control systems we don't like it in terms of performance? What will happen? Or did somebody tell you why do you need a controller anyway? I can just simply close the loop. Why do you need a controller? One at a time, guys, because remember the same thing I said. So why do you need a controller? To have the desired performance. So even the system is stable, it may not provide you the right performance. And how do you define performance in a control system? How do we define performance? Huh? How do we define it? Yeah, performance indices. Let's say very simple basic is there is the transient performance, there is a steady state. Transient is overshoot, undershoot, settling time. Steady state is basically steady state error. Don't forget that. Those are undergraduate material. So those are the performance. So open loop, even though the system may be stable, you still need a controller in order to make sure that it maintains the performance. So open loop systems may not meet a certain performance. That's why you need a controller. Don't forget that. Okay. So here the system, even though physical system is deterministic, because of the network it becomes stochastic. the overall system. So this was discovered. So all of us were struggling. So this was one of the classical papers we published in Automatica that models the whole system into a stochastic, and you will see that hopefully tomorrow. So here is a simplified representation, and here is the paper that I cited, published in 2012. And you know what? Most of us are familiar with linear systems. I'm going to show you that. So if I have a linear system, a continuous system, x dot equal to ax plus bu, okay, and if I have to bring in the network delays and packet losses, then I do a little mathematics here, okay, and I bring in all that stuff and I'm discretizing it, and you can see that this operator equal to 1 when x is greater than 0 equal to 0, there is a bound on delays. So if I do the mathematics, then the same linear system becomes discrete. Look at that. It becomes discrete. That is a model or a behavior of a network control system. So when you model it, it becomes discrete, and you see that the A matrix here, the A matrix is a function of delays. You see that D bar is a delay, and the gammas are packet losses at the time instant k minus 1 k. So that model, A and B matrix, becomes random and stochastic. When I say stochastic, it's a function of random variables. What are the random variables? The random variables are network delays, packet losses of the network. Even the computer science guys doesn't know this, or even communication people. So this is what the technology is. So now look at that. This system that I showed you, this is the deterministic system, A and B matrices. When I'm enclosing it by a loop, and AZK is a discrete time A matrix with random packet losses and delays. So unless you have a mathematics, you won't be able to do this. And the mathematics is here. So it requires a background on stochastic, requires a background on linear algebra, it requires a background on digital control, where you take a continuous system and you are discretizing it. You need to really have to have the background like this in order to take that equation 1 and convert that equation 2. And you see the B, this B is also a function of the packet losses, and D. So we were the first ones to show the world how to model this. So you see how this guy, a Chinese guy, is a very famous guy, and that is his PhD work. He's known for that, and that's why he's this author of the book. That is his PhD. He's written 17 transaction papers. So you see that a PhD, how it comes out. Yeah. So each of my students, a PhD student, has a legacy. He goes with some name, like his area was network control. So that's how he becomes an expert. So this is his work, fundamental work. How? So until then, nobody knew how to take a linear system, and people were doing all ad hoc stuff. But how to take a linear system and actually have these network protocols, how does that work as part of a network control? So that's what we're going to use in your labs. Yeah. And this since is a random variable, the packet losses delays, you have assume a distribution. And they vary in that distribution. Since they're varying, this A and Z also will be varying. Now let me ask you one question. Do we know the delays and packet losses? Do we know the delays and packet losses, guys? Do we know gammas? So D bar is the delay, gamma is the packet losses. Do we know that values? We don't know that. You can assume a distribution. That's what I said, the assumptions. You can say it's a normal distribution or some other distribution, right? The random delays and packet losses. But then since those are varying, what will happen to AZK and BZK? Even though my A matrix and B matrix, I know very precisely from the process that I'm controlling it, I want to control. But AZK and BZK, I don't have any clue. Why don't I have any information? Because the gammas, you see that this is at k minus 1, the delay at k minus 1, delay at k minus I. So the k minus d bar is the time. And those, the gammas can vary over time. So therefore, I don't have the AZK and BZK. I don't know. I don't know simply. So even though I know A and B matrix very precisely, at the end, I may not have AZK and BZK. That's the problem. Okay? So when gamma becomes, when there is a loss actuator, it becomes open loop. When it becomes open loop, the gamma becomes 0, so some of those values will become 0. The system will become open loop. Remember that. Okay? Any questions? What is a network control system? You see that now. So because of the network, okay, so because of this network, you see that this controller information doesn't go through to the actuator. And because of this network, if there is a packet loss, the sensor information is not fed to the controller. So therefore, the controller and the plant, even though they are connected by a wire or wireless, nothing is going through the network. It becomes open loop. Okay? So this is what is called a network control systems. So the losses, packet losses, delays, the delays are random delays. That's why it's become stochastic. Any questions here, guys? Any questions? So AZK and BZK, you don't know. We won't have that information. So controller. Like you designed, like, root locus and all, right? Remember that in undergraduate? I know some of you are masters. Did you guys take a state variable course? Right? So when we design, do you guys know Ackermann's formula? What is Ackermann's formula? That's a danger. You nod your head. What is Ackermann's formula? That's correct. Go ahead. What is Ackermann's formula? So Ackermann's formula is U equal to minus Kx. Okay, or K times C if it's an error. Right? So K is the feedback gains. Very simple. Feedback gains, right? So now how do we determine the feedback gains? How do we determine them? Pole placement. So how do you place the poles? Now hold on, let's look at it. How do you place the poles? How do you come up with the poles of a system? But that is the desired pole, locations of desired poles. But how, you need to know where the location of the actual poles are. From the roots of the characteristic equation. So that means you need to know precisely the dynamics. If I don't know the dynamics, how are you going to come up with that? You see? So I cannot design a controller because I don't know the system dynamics. So if I do let's say by chance if I try to come up with a transfer functions, right? That's what we normally use. If I don't know those locations of those A1, B1, that means I don't know the location of the poles. I can't come up with a design. So you see that that's the PhD problem. So if you're a PhD student, you should be looking at problems like that. So it's a linear system, and even though it's a linear system, basically I don't know those dynamics, so that's where you got to use what we call adaptive control. And adaptive control, what it does is, it estimates something, and then using that information you are controlling it. Okay? But there's a difference between learning and adaptation. Nobody is going to tell you that, because nobody knows that. I'm telling you right now. Somebody who worked in this area knows. So what is the difference between learning and adaptation? We all do that as a human body. As a human, we do that. We learn and we adapt. But what is the difference? What is the difference? And what is learning? What's learning? Guys, this is not a simple question. Even faculty, many of them don't know the difference. I'm telling you. So what is the difference? A learning and adaptation. Because in adaptive control, as some of you said, right? So what do? You assume A and B are known, and you basically estimate it, and then you use it in the controller. That's what we normally do in a traditional adaptive control. But, so then why are we using machine learning? What is the difference? Okay, this is your homework. So you're going to come back and tell me tomorrow. I'm not going to tell you today. As I said, a lot of faculty don't know. 90% of them doesn't know, even control. No, you can still do the same adaptation. Adaptation is supposed to do that. Okay, so that's not the reason. That's why I said 90%. You can check with your advisors. I assure you, unless they've taken my class or something. Yeah, this is what the skill set, what I'm talking about. There's a huge difference between learning and adaptation. Yeah, okay. So we'll talk about that. I won't go without telling you the difference, okay? All right. So there is also stuff that can come in event triggered, and at the end of the course we talk about that as well. So basically the problem with these networks are, these networks you can see has a finite bandwidth. So there's only so much you can send. You have a pipe. A network is like a pipe. You are sending water through it. There's only so much water you can send it. And how much water can you send in the pipe depends on what? How do you determine how much water flows through? A capacity, but so what is that in volume? Remember that? So there's a capacity that how many packets go through. It's very similar. So most of the networks have finite capacity. And if it's a wireless network, it's even less. So when you don't, if you're sending a lot of samples, because you're sampling at a very high rate, then you're sending the same feedback, like sensor going through the network and the control packets going through. Sometimes the packets can get dropped because it has a finite bandwidth. Okay, so don't forget that. Okay, so what will happen is there's a new type of control called event triggered control. So typically we assume that the sampling rate is determined by Shannon's minimum 2 times that, and in control they say you basically determine by 10 to 20 times the closed loop bandwidth. Okay, this is kind of ad hoc. So event triggered control basically kind of threw that out and say they call that as a performance based sampling. So what it means is basically I can leave the system in open loop, and the minute the system is becoming unstable, then I suddenly close it. So by doing that, what is the benefit? What is the benefit in a network control system? You can reduce how many packets are going through the network. Right, you see? You can reduce. So right now you can say 10 times the bandwidth, you can still be in kilohertz. Sometimes, that means you are sending so many packets and you don't really need it. So, so now this particular one, event triggered, you see that there's a network. If the sensor is constantly transmitting, and instead of doing that, you have a switch. The switch closes and opens based on that performance. And by doing that, you can still show stability and the same set of performance. That's called event triggered. So you have an event based on certain performance, and it basically closes the switch, then it basically you transmit a packet. There's a lot of work happened in event triggered. That's a separate book that came out last year, 2024. There's a book that you can look at it. Yeah, all right? So you can see that here, you see these are spaced at equal intervals. This is what we do now. And here you can see the duration varies here. This is called event triggered control. Okay, there's a lot of work going on now. You know, it's now older. It's basically a old technology now. Okay, so they use what they call a zero order hold. It's called zero order hold. It holds the value until a new value comes in, and then you basically, you know, do that. Okay, so I'll skip all this. You see that this is the Ackermann's formula. U equal to K times X of K. All right. Okay, so I'll skip all this. So let's go into let me go into another set of slides. So now I'm going to go into, that's a basic introduction of network control systems. So while I'm pulling up the real reinforcement learning, do you guys have any questions? Do you guys have any questions? What is a network control system? That's what I explained. And it came out from cyber physical systems. So if you talk to people in cyber physical systems, people know that by now. Okay? So cyber physical systems has got a lot more stuff. But network control is basically the small stuff that for control people. So yeah. So what is any questions on what I just covered so far? Tomorrow there will be a lot of stuff goes very quickly with mathematics. So you may not understand everything, let me tell you. And don't even imagine that you will try to understand it, because you learn major things. You have to take a formal courses. So I'm going to, in this one, I'm going to cover a few other basics. Okay, any questions? Yeah, go ahead. D-bar, some delay bound, because you really don't want the D-bar to go to infinity. So why is that? What will happen when D-bar goes to infinity? It becomes open loop and you are not really closing the loop. So basically you cannot operate a system open loop. Remember, if the system is inherently unstable, then you really need a feedback. So you can make the system stable, and that's why the D-bar has a finite value. You know, the bound is finite, but within a bound things can vary. Any other questions? Yes. That's correct. Right. So you can even still consider the network control system as a different time scale, because you know, you could even there is in stochastic control, stochastic systems, there is a stationary process. Remember that. There's also non-stationary. What is non-stationary meaning? I know we studied this in undergraduate. All of us do that. But you know what happens when the math professor teaches that? It goes above it. We think, oh, it's not needed. So stationary, what does it mean by stationary? Even in stochastic processes, we study that. What is meaning by stationary versus non? And that's what I'm coming. So what is, to answer your question, what is stationary, what is non-stationary? Stationary means it's not changing over time. Time invariant is basically in stochastic. They won't call that as time invariant. They call stationary. That means you take any piece of time, the properties of that would be same as any other. So the same behavior, what happens is you could have in the process multiple levels. Each level might be operating, one of them is operating once an hour, other one is operating in milliseconds. You see? Yeah. That's where the time scale is coming in. Any other questions, guys? Any other questions? And don't feel shy. Let me say this. I don't know. This is something I learned. I never ask questions. I used to be very shy, and I realized that some of the questions, probably what I was having in my mind, were very difficult. So I'll tell you something I learned in my so many years of faculty life. As somebody who is asking, you think that guy is dumb. Sometimes those questions are difficult to answer. You'll be surprised. Yeah. So quantization means, let's say you have remember, then computers operate a certain number of bits, like they have byte, right? So let's say like you are using 8086 processor or like a Pentium processor, they have a certain word length. So sometimes it's a 16-bit, sometimes it's 32. So you take a value like a temperature or a pressure and you are digitizing it in the number of words, in the number of bits. That's what is quantization. So you don't have infinite number of bits to quantize that value. 1.66666, let's say. So round off, right? You round it off to 1.67. That's basically what is quantization. We're going to talk about that. So we'll do that. Quantization is one of the chapters, we'll look at it. You see? And that creates some error. Okay? So that's an additional thing that, so you're taking, you have a finite thing and you are writing that, let's say 1.66666 something, you're truncating and writing as 1.67. Yeah. Okay, any other questions, guys, before I get into reinforcement learning? So this is how it quickly goes. Okay, because it's a 2-week class, that's basically. There's a lot of stuff behind, we talked about it. So don't forget, you may want to think about it, what is the difference between learning and adaptation? Okay, so you ask or you Google and you come back to me. And I want to see that, okay? So any other questions, guys? Okay, so I added this topic, it was not in the lecture, because I realize many of you probably won't know much about reinforcement learning and stuff. So unless you take a course on some neural networks or machine learning, how many of you have taken a course on neural networks? So no course on neural networks. Do they offer here NIT Rourkela? Okay. No. Okay. So we do offer that, and it's a required course in undergraduate. Neural networks. So even computer science they do offer. Yeah, it's very important. So we'll talk about this, okay? And this will gives you some background on reinforcement learning. So there are 3 forms of learning. Remember, I am told you what is the difference between learning and adaptation. Okay? So I'm just going into, that's how people do. Remember that. All right? So there are different forms of learning. One is called supervised learning. That means somebody is teaching you, holding your hand, and you know, remember when you have a small child, you hold the child's hand and we write, right? Namakarnam, we basically write the name. So that's called supervised learning, okay? So people use, these are targets, okay, and P1, P2 are the actual output of the network, right? So basically the goal was the actual output should be close to the target values, okay? Then we know the network has learned. Now the targets, people use that, we call targets, the computer science guys call labels. So if you talk to people in computer science or AI people, they talk, do you have a label? So label means basically a name or a target value. Okay? So you need that in order to develop what we call supervised learning. So use the error and then you're adjusting the weights of the network, and that's called supervised learning. A reinforcement learning is a classroom environment. Now, you have taken courses, right, in NIT Rourkela or some other place. Now, a professor or a teacher teaches you something, then how does he assess whether that material is understood by students? How does he do it? You're conducting exams. Now, those exams are not holding your hand. Remember that. He periodically say, in my course, you take 3 exams, you have 10 homeworks, right? And the homeworks are basically graded a little more frequently. The exams are fewer, right? 3 exams or 4 exams, whatever, and you have a final exam. So what do? You get a grade, and then once you get a grade, what will happen? Somebody gets 60, somebody gets 90. So what is the difference? What's the difference? 90 out of 100, that's what I mean. What is the difference? So in terms of performance, somebody who's getting 90 means he's doing better than somebody is getting 60. And that's what is reinforcement. So what happens if somebody getting 60 immediately has to have a different plan. So let's say in the first exam that person didn't do well. So what does he has to do? In the second exam you better prepare something differently, so that your score will be from 60 to 90 or whatever. So that form of learning, it's not like holding somebody's hand and you are adjusting. So the professor won't tell you, right? I won't tell you what you need to do. And what I tell you may vary from one student to the other. Okay? So I can tell you something, but that may not apply to somebody else. So that basically is called reinforcement learning. So you're really not told how to do it, but you will be given a score and you use that information and you have to adjust yourself. Humans do all the time. All biological organisms like snake or baby. So how does let's say that baby or something, remember when we were babies you touch something hot, you remove the hand. So who tells them that it's hot, you need to remove it? Who tells them that? Who tells them? Nobody. It's a reflex. Sometimes people call that as a reflex. So a lot of times people learn differently. In each of you probably I can't expect you to learn everybody the same way. All of us learn differently. Just like all of us have different height, different weight. Yeah. So reinforcement learning, we'll talk more about it. Unsupervised means you have different outputs and you cluster them, different forms, like you can say all women have certain characteristics, all males have certain characteristics. So that's basically we cluster them, or people with different height, for example, you can cluster them, different weight, for example. So that comes under what we call unsupervised. So there is no supervision, but you basically do. Reinforcement learning, the only feedback is the score, how well, or 90%, 60%, what I told you. That won't be continuous. That is the score, you get it and you use that information to adjust your strategy. Okay? So there are three forms of learning: supervised, reinforcement, and unsupervised. Now in control, we talk about online learning. We'll talk about it. So a lot of supervised learning is offline. The supervised is offline. Reinforcement learning is also offline. So that means it's not done in real time. But in control, we need to learn the dynamics in real time. So we do what we call real-time learning. We'll talk about that. Real-time reinforcement learning. Okay? So what is reinforcement learning? When an infant plays, waves his hand, or looks about it, it has no explicit teacher. Remember, you look at a child, who is born, after a few months, the child, you smile, the child smiles back. Who is teaching that? Nobody. Probably some of you are young. When you have kids, you'll know. Yeah, you don't teach the kid. It smiles. This is very interesting things that you do, right? And you wave the child with a hand. You will realize that the child waves back. You're not teaching the child. Sometimes parent may hold the child and you wave. But over time, the child waves. So nobody is teaching that. Exercising the connection inside our brain creates a wealth of information. That's what is happening. Now remember, when we are babies, you ask your parents, if you feed a baby sweets, there's a smile on the baby's face. You will see that. You feed something sour, the child will not take it. You don't have to. You try it out. So a lot of medicines, they put little sweet in there. This is because of that. So that is basically generated. Nobody teaches a baby, this is a sweet, this is hot. Nobody. So all that happens with a natural snake or even dog. Yeah. Nobody teaches that. We all learn by ourselves. Try it out, guys. You work with psychologists, he will tell you more than I do. Okay? So what we do is we study the computational side. How are these connections are formed? And we call that as learning. Okay? So a reinforcement learning from interaction. So I'm interacting with an environment, I learn from the environment. And it's also called goal-oriented learning from interaction. Okay? So what is reinforcement learning? Problems involve learning what to do. But you don't tell them how to do it. Remember that I told you. A supervised learning, you show them how to do it. But in reinforcement learning, you only do what to do, but not how to do. So how to map situations to actions to maximize a numerical reward. This is what I told you. If the student gets a 60, he has to think about it. How should he make a 90 next exam? And no professor can tell you. You can say, oh, you study more. But that's all you can say. But he won't tell you how to study, how to solve problems. So these are closed loop problems, because the learning system's action influences later inputs. So this is what we use. A reinforcement learning is like a closed loop control problem. The learner is not told what actions to take. This is exactly what I told you. As in many forms of machine learning, but the student has to discover based on his own IQ. Okay? Actions may affect not only the immediate reward. So that means that if I'm studying for that exam, I may do well, but I may not do the next exam. You see, but they're all connected together. Materials from one exam may be connected, right? That's important, okay? So it is very important. So what is characteristics of reinforcement learning? It's a closed loop system. Not having direct instructions. So nobody has a instructor to tell you what to do. They won't hold your hand, unlike supervised learning. Consequences of actions have a real big issue. If I make a mistake, it could be dangerous. Let's say that you learn driving, right? The instructor tells you, okay, you take a left, you turn the wheel, right? But remember, if you make a mistake, what will happen? You may hit something, and if it's a human, you may die. The guy may die. So it could have a serious consequences. Okay? It's often interactive. Interactive means you interact with the environment, like you are driving in a busy street. They'll take you when you are driving, and then you'll tell you take left, turn right. This is how they teach you to drive. Okay? So we call that as an agent. An agent must be able to learn from its own experience. So he can only teach you so much. Most of us ride a bike, right? In childhood. Somebody is teaching you for a few minutes, a few hours, but then after that you practice, right? And you learn. Sometimes in a hard way. You go and hit somebody, then you fall, you learn, right? So you don't really want to do that. Okay? So there is also called exploration where exploitation in a reinforcement learning. And we do all the time. Humans do. So let's say you go to a new place. What do? You explore. Even if you are in the same place, I'll tell you. And if you have multiple routes, sometimes you take a different route because let's say there's an accident. Oh, you realize that, man, I'm so fast. There's nothing here, no traffic. So unless you explore, you won't know that. That's a better route. So in reinforcement learning also the same thing. You explore, but unless you explore, you don't know. So exploit is basically what we call greedy path or greedy solution. That means that you have driven that route and you know that that's the best route, right? But unless you explore, you don't know whether there's any better one. So explore and exploitation. Exploitation means a greedy. That means already you have learned something out of it. Explore means you don't know that and you're trying one out of multiple. So this happens in reinforcement learning. Sometimes during exploration, you fail. You fail. So let's say you're controlling a plane. Do you really want to fail? No. Yeah. That's a big thing with real time. Remember I said that in my comments? So this is why there's a difference between the people who talk about AI and the people who talk about AI in control systems, because it's very dangerous. Okay? The same thing with reinforcement learning. So you have to really think about that part. So you have to discover actions, but you also have to try actions that I have not selected before. But if you select some actions, that could be disaster, right? So agent has to exploit, and then he has to see whether the reward he's getting is better or not. If he gets a better reward, that means it's a better route or whatever, right? So the dilemma is neither exploration nor exploitation. Now, neither one of them you want to do it. You have to do both of them at the same time. Okay? So agent must try a variety of actions and progressively favor those that provides the best reward. Reinforcement learning is a separate course I teach. It's a full semester course. Okay, so I'm giving you in about 45 minutes. Okay, so it's a stochastic. So that means you start at different times, you get a different result. So it's all this learning is always stochastic. Okay. Key feature of reinforcement learning explicitly considers the whole problem as a goal-directed agent. So that's very important. So in a reinforcement learning, the goal is something, right? I need to do well. So what is your goal if you're a student? Is to get an A in the class. Now, is that the goal? No, you shouldn't be getting a goal like that. What is the goal, guys? What is the goal? Huh? To learn the material. But you know what? It's statistically, people have shown that 99% of the students don't have that goal. Do you know that? What is the goal if most of the students do? To get what? That's all most of us do. All of us say that I want to learn. Remember I asked you this question. What's the difference between learning and adaptation? We adapt because we look at what the professor is going to ask. You look at previous exams and then you work out some problems and then you adapt. But you don't learn. So I know that's exactly what you need to. But none of us practice. I'm telling you right now. Yeah. That's the big problem why we are not successful. There's a big difference between learning and adaptation. Remember, I keep giving you will see that there are plenty of examples. Yeah. There's a huge difference, guys. You can get a grade. I'm telling you right now. It's easier, but it's very difficult to learn the material. When I say learn, there's a difference. So, you know what happens usually, when you really learn, I don't know in your student life, can somebody tell me? At least I didn't learn when I was an undergraduate student. I was the topper. But I really didn't get that enlightenment. That's called enlightenment. Till I started doing my PhD. Yeah. So that's when you really learn. There is an exam. I don't know in these universities here. We call that as a qualifying exam. So in the qualifying exam, the students have to take in the second semester that exam. And it tests all your undergraduate stuff. All your undergraduate. Okay? It's closed book, closed notes. You can't bring anything. You can only bring a regular calculator. No programmable calculator. So one full day exam. Okay? Is that easy here? Even in IITs, I never heard of that. I think you should take that. And you know what? When I took in Georgia Tech, 1/3 of the students only pass it. We also have comprehensive, but that's different. I'll explain that also later. So qualifying exam you got to have. That's a mistake a lot of us do here. I'm telling you that. So there are, let's say I took my exam. When I took that qualifying exam, the department says that you have to take it in the second semester. So you have to, all of us have to take it in second. So if you start in the spring, you have to take it in the fall semester. Okay, that's the second semester. If you start in the fall, you have to take it in the spring. No options, okay? And 250 students normally take, when I took that exam, about 45 to 50 students pass the exam. They give you 2 attempts. Once you have failed in the second attempt, you're out. You take your master's and you walk off. You won't become a PhD. And it'll test all your undergraduate. All your courses in undergraduate. You have some choices. Okay? You have some choices. So they'll tell you, you can pick 5 topics out of, like in electrical engineering, you have circuit